Okay, so hello. Today we want to talk about Dream 3D and how we can use that to create our own virtual or close to reality representative volume elements or microstructures for different use cases, just for visualization or for different kinds of simulations, for example, like crystal plasticity simulations. We will be using Dream 3D to um, do that. If you will open up Dream 3D website, or for example, if you will just search on Google Dream 3D, this website on the top will pop up. If you will click on this, you will come to this website. They've recently launched this Dream 3D NX version, right? Um, which has some extra features, but because I've been using the older version of Dream 3D, so we'll be talking about this case, right? And what you will see is that if you will go down on this page a little bit, you will see that they have different downloadable formats, right? So you can download it for Linux, you can download it for Windows, and for different for other different operating systems. If you will click on this, you will download this one file, which you can then use to unzip, and probably you will have to download, you will have to install it on the system. If I'm not sure, or maybe there is a bin folder in which you just go and there is an executable file there. But somehow you will be able to uh, find out instructions on how to install it and how to run it from their website, and in the end you will reach um, um, you will reach this here. So if you run Dream 3D, it looks something like this. Maybe your data structure, so your pipeline is maybe on this side, your data structure and your filter list is on the other side, and maybe some of this is not visible, but you can always go and view and click on all these to view all of them or hide any of these. But what I feel is that all of them are important structures, so you will need them somewhere on your window to actually function better, right? And then I just want to start with about Dream 3D. So what you will see is that here I am using Dream 3D version 6.5.121. It is very close to the recent version of Dream 3D without a visualization that they launched, and then after that they visualized NX, which I'm not using here. So whatever we will be doing is true for this and for any other um, for a similar tool that you will be using. Um, okay, so how they have built Dream 3D is that they've they have this pipeline here. So you have different blocks here, right? And from these blocks you can whatever. Now, for example, stats, right? So you can, for example, something like this. You can import this block here. You can click on this, and then you can start working on it, right? And then this will generate some data, right? So here, for example, you will see data structures. There is a stats generator data container here, and if I will do something, I will create data, right? You will see that this data structure will get populated. So this will generate data. It will be visible here, and then we will want to do something with this data, right? So then we will have another pipeline um, section, which pipeline component that we will copy from here, paste here, and then this data will be processed, and on and on and on until we will reach our desired state or value. So this is how basically it is constructed. What I like doing is I do not start with creating my own pipeline. It takes a lot of time, right? What what people in Dream 3D have done is they have tried to see what are the practical use cases of Dream 3D, and they've tried to construct these virtual pipelines for almost all of these cases with a very nice documentation. So they've tried to show all the examples how you can use that. We will be starting with one of these examples, okay? So if you click on File, if you click on Open, in your Dream 3D installation folder, right? So mine is in the software Dream 3D 6.5.121. You will see all these folders, okay? And I want to go in this folder of pre-built pipelines. In this folder of pre-built pipelines, I want to go in the folder of, you can go in all the other folders. I want to go in workshop and click on synthetic. And here there are different JSON files given. These JSON files are primarily um, the constructed pipelines that give you certain outcomes. And with the names, you can see what they are doing, right? So there is single cubic phase equixt. Okay, I will just open this. When I open this, it opens up in a new window, right? And then you will see now there are a few more pipeline components here. Okay, and then this basically will create a single cubic phased equixt representative volume element that we will be able to use. Okay, what I do is I will try to save this Dream 3D file in one of the folders. So what I will do is, let me find somewhere nice where I can simulations, softwares, us. Um, I will create it here, new folder, testing, Dream 3D RVE, testing, Dream. So I have created this folder. I will go here and then I will write the name single phase. Okay. So my pipeline has been saved. I do not want to save it as a bookmark. Um, and okay, so we start from here. The first thing is you start with the stats generator. Okay, so imagine you want to create a, a virtual representative volume element, and in this window you fix all the statistics of this representative volume element. What will be its grain size distribution? What will be its grain orientation distribution? What will be its grain shape distribution? And we are always talking about statistics. We are not talking about one value. We are talking about the distributions. Okay, and what we do here is, for example, because we only have one phase, it is named as primary. What we can also do is we can change this name to whatever we like. If we write, okay, we can do that by clicking here and doing this. I will not click on this plus, because using this we can generate other, you can generate other microstructural features. I will not be talking about that right now. We will look at this window. So this window gives you an idea of what is the mean feature estimated sphere diameter. Okay, so basically what it means is if your grain has a certain volume, and you can it will be of a complicated shape, but the total volume can also be compressed um, um, into the shape of a sphere. If the equivalent sphere has the same volume as your grain, what will be the diameter of the sphere? So basically what it is fixing is the size of the grain. It can have complicated shape, but what will be its size? Okay, and what we do is, by changing this estimated sphere diameter, we will change the grain size theoretically, right? And what we can do is, you can go to the documentation and you can see this is a basic equation for the standard distribution. And basically what I can do is, I want to change this mean feature estimated sphere diameter from 10 to, let's say, 5 initially. So I'm trying to do that, just playing with it. I will try to do it too. Yeah, it comes down. I will try to do this as 1.5, 1.6. Okay, sigma is 2. No, 1, 5. Yeah, I want to change the bin size to 1. Okay, and then you, for example, you see what is the minimum and maximum cutoff. I want to reduce the minimum cutoff. Okay. Um, and with this, for example, you see, I have to change this. Yeah. Yeah. Okay. So you see that with mu, we are basically changing the mean of this curve. With sigma, what we are doing is we are controlling its shape. So is it equally distributed or is it skewed in one direction? With minimum and maximum cutoff, we just control where does it begin and where does it end. And the bin step size is basically the step size of this one bin, right? So for example, now bin size is 1, which means it is equivalent to 1 unit. If I reduce it to, for example, 0.5, you will see the number of bins increasing. So this just means more population of grains in one bin, right? But that is how basically we control this distribution. And this is just the distribution of the grain size. Okay. Then, for example, you will see the distribution of probability density function B by A and C by A. B by A and C by A are primarily the um, the grain size functions. We do not usually play with omega B by A, C by A. With neighborhood distributions, you can see that how many grains will have how many number of features neighboring them. We also usually do not play with this, but maybe you have special requirements and then you do that. Orientation distribution function is quite interesting and important. We want to have an orient. So a few things that we fix um, few things that we really fix that are really important and we fix in our microstructure are the overall grain size, the grain shape. So are they equiaxed or are they elongated in a certain direction? And then the third thing is associated texture to them. So what is their orientation distribution function? Here, for example, if we have a random orientation distribution function, we generally go with, for example, this kind of initial value, right? So we say it is just a random distribution function. We do not have to do anything about it, and we go on. But on the other side, for example, if we want to have a certain orientation attached to them, what we can do is we can choose, for example, copper, weight, sigma, okay, and then, for example, we will have copper type microstructure. Or, for example, we can delete this, or we can have brass type microstructure, right? So for example, we can say load from a bulk file and then we give input of this file, and from here, for example, we can change that. Initially, we will talk about this later as well. I don't want to spend more time here, but the idea is that from here we can change the orientation distribution function. There are multiple options available. I can either input it in terms of Euler 1, 2, 3, their weights and the sigma attached to them, or I can directly load it from a bulk file. Either way, I can change this orientation distribution function. Also, there is a way of representing it in the terms that we are usually more familiar with, right? In terms of this distribution, um, this color distribution rather than this discrete distribution that that is that can be read here, right? And then another thing is axis orientation distribution function. Now, this axis orientation distribution function is basically again uh, the how the grains are elongated or not, right? So for example, if I choose primary rolled, and then I can say, for example, axis A length is 5, axis B length is 2 and 2. right? And if I do that, we will see some differences. Oh, create data, reset. Oh no, but we will come back to that. So axis A, B, C can have different um, access values. Um, I still have to see how to do that. Memory equexed. Memory rolled. No, I think we put these values here. But anyways, so this basically controls the shape of the shape of the grains in certain direction or orientation. What we do here is once we have the strats generator done, what we do is we create data here. Now again, when we click on create data, what it does is based on all the inputs in all these conditions, it generates data structure, which can then, for example, is input here. Now when I did click on reset, it changed to mean feature ESD 2.7 instead of 5, but it's okay. We will just have smaller grains. Okay, let's go to the next step. So this step depends on the input from the previous structure, which is about initializing synthetic microstructure size. Now, the dimensions of the microstructure are what is the what is the you get decided on your own. For example, it can be micrometer. So then it will be what is the size in terms of micrometers from one edge to the other. So for example, X, Y, and Z. If I say, for example, it is 100 by 100 by 100, or I will make it smaller to run simulation faster, 50 by 50 by 50. The resolution is how is this 1 point resolved, right? So if resolution is 1, 1, 1, this means 50 points in X direction, 50 points in Y direction, 50 points in Z direction, right? I can still have the same dimensions, but I can resolve it using, for example, 0.1. Um, this means 500 points in X direction, 500 in Y direction, 500 in Z direction. And then origin is we want to place origin at 0, 0, 0. And what we do is we do not have to fix anything. All the names are already written here. We take them by default. We go to the next step, right? And then, for example, here we are establishing different shape types. Okay, so for example, here we are saying we have ellipsoids or super ellipsoids or cylinder A, B, or C or cube octahedron. If we want to have equiaxed microstructure, it is quite easy to, let's say, start with ellipsoid. We will just stay with this, stick with this, see the answer at the end, and then we will decide what to do. And then this is a pipeline for pack primary phases. What happens is that we want to create data, then we want to initialize synthetic volume, a specific size of the RVE. Once that is done, then we want to establish shape types. Once these shape types are established, then we want to pack them in that and in that volume, right? And what happens here is that it is basically an iterative process. So it will try to generate grains of different sizes while still remaining in the statistical distribution that we gave, and then it will try to fit all of them in this volume container that we have created. And once all the conditions of the statistics will be satisfied and the whole RVE will be packed with all the features, it will converge. So that means that is the solution that we intended, and then it will then we will go on to the next steps. And it is basically an iterative process. There is one thing that we usually, from the crystal plasticity perspective, we like is we want to create periodic boundaries. right? So we want to have the same grains on this end than on the other end. So then when we um, when we run, for example, crystal plasticity simulations with um, periodic boundaries, periodic conditions, the features on the boundaries are not misaligned with the neighboring atoms, with the neighboring features, and the results are not distorted. So we click on this, so we will have periodic boundaries, and then this is also, for example, just an iterative process to find feature neighbors, to fix position of every feature. Then we say match crystallography. Maximum number of iterations possible are this. It will automatically fill in all these objects and so on. We want to create IPF colors. The question is, how are you creating your IPF colors? The reference direction is 001, which means um, the IPF colors will be generated from the Z direction perspective, right? What I want to do is, if I want to create them from the X direction perspective, I have to do this myself. I have to click on 100. Okay, so now I have generated features from 100 perspective. So we will see. So in the x-axis, the IPF colors will be generated from the x-axis perspective, and then we have this block of write dream 3D data file. It will also write XDMF file, um, and the question it is asking is, where do you want to write this file? Okay, I will select the same folder I chose to save these files to, and I want to put it here, and I want to name it single phase 1, right? Just single phase 1. Um, and then I save it, and then what I will do is I will run this uh, calculation. So what it does is, what you will see is, what it does is it takes time to, if I will go up, what it takes time to generate features, right? It takes time to generate features, then it takes time um, to match this crystallography and to pack primary phases, and then it will go on to the next step. It is taking quite a lot of time, and the reason is because our RVE size is quite large and our feature size is quite small. What I will try to do is I will try to avoid this, and to do that, what I will do is I will still then now increase this size, right? I will create data again, and then I will start. Oh, I don't want to do create data. I will do this again, and now we will see it takes much less time to pack less number of features, right? I want to go in the folder that I am working in to see what are the outcomes. Okay, so this is my folder here, right? And now it has one JSON file that I saved, which is my project file, my pipeline. And then it has exported two files, Dream 3D file and XDMF file. So this Dream 3D file basically contains all this data that is recorded. Sometimes we do not want to run this calculation. We just want to use these features in the next step. So then we can just import this Dream 3D file and continue working with that. But sometimes when we want to create this new file, then we can always run the simulation and we can change that. But the important thing is it has also written XDMF file, so I can visualize this. I will double click on this, and it will open in my ParaView. You can download and install ParaView on your own system. by just searching for ParaView on Google, and you will find that. But what you will see is I am running ParaView 5.9. The newer versions of ParaView will look very different from this, and they will have new features, but the basic concept or the idea is same. Okay, so what I have here is I have this ParaView where I have this file imported. By the way, what I can also do is I can just, for example, delete this, and if I open my ParaView, I can just drag and drop this here, and XDMF, just open XDMF reader file, and this file is here again in my pipeline or built-in. I click on this small icon here on the eye, and then I'm able to see this cube, and this is just the shape, but I know that it is 100 by 100 by 100 dimensions, and I want to see the surfaces. Okay, so these are the surfaces, and now I want to see my greens. What I have to do here is if I click on how do I color this, solid features, I can click on, for example, feature IDs. So all these features, basically features means grains, have different IDs. So there will be feature 1, there will be feature 200. So they are colored based on their feature number, and what we see is this rough structure of grain size. It is relatively low resolution, but we see the distribution of random eqexed grains in this case, right? And now we want to see their orientations according to the x-axis, right? And the x-axis in this case you will see is in this direction. So from, if we look at this from this perspective, from this face or this perspective, what does their orientation look like? For that, what I have to do is there is this setting here, right? So if this is not clicked, you have to click on this. So then you get some, see my slide bar. For now, I have very limited options or possibilities to manipulate. But if I click on this, I get a lot more options and I can manipulate several things. So this should be on. If you will go down, you can, for example, click on map scalars, and then it will not map scalars. It will show raw 3D data. I can click on IPF colors, and now it is showing me IPF colors for the cubic crystal structure on this uh, inverse pole figure map from the x direction, right? And for example, now I see that this is a 001 oriented grain, and the green ones are the 111 oriented grains. So something like this, right? The IPF color maps that Dream3D uses are also available with its documentation online, and you can use them to translate that. But for example, that is how we generate a representative volume element. What I want to do is I want to go back and try to manipulate some of the features to see what does it result in here, right? In this single phase microstructure. I will go into the stats generator. What I want to do is I first, so the first thing is I want to increase my synthetic volume size. So let's say I increase it to, or I keep it 50. I keep it 50. I want to decrease my resolution to 0.1 or 0.2, 0.2, and 0.2. Okay, and then I start the pipeline. It takes some time, but it is again basically overwritten here. So what I will do is I will have to somehow this here as well. And now if I see this outcome, so basically it should be more um, resolved. Oh, it made it smaller. Hmm. Okay. Not what I Not what I expected. So if the resolution is 0.2, 0.2, 0.2, what it does is multiplies this with 0.2 and the overall size reduces. I want to keep it 111. I just want to make this 100, 100, 100. Start the pipeline. Oh, I think I should increase the resolution instead of decreasing it. Um, this is basically confusing. So I think what is expected here is that you have to increase this size. So if I say 555, that means then there are more points in the same size than the other way. But yeah, it is already complete. We will see what we get at the end. So now I have tried to change this. I have tried to change the size, and we will see what we get now. I will delete this. Didn't help. I will try to bring in this HTMF reader. Surface feature IDs, and then you will see because I've increased the size, so there are more number of grains in this representative volume element. What I also want to try is what I will, if now, for example, I increase the size, right? So what will happen in the same representative volume element, there will be less grains because now the grains are bigger. Make sense? So previously it was 2. So equivalent sphere diameter was 7.4, right? If I increase it to 3, now the equivalent sphere diameter is 20, which means the grains have a bigger diameter, the grains volume is bigger. But in the same synthetic volume size, which means now there will be less number of grains. 0.1. The other thing that I want to try is I want to modify the orientation distribution function. Instead of just using this random orientation distribution function, I want to I want to use this cube distribution function, in which you will see that the distribution is like this, okay? Which means that from the 0, 0 okay. Is it now okay? Okay. I'm not sure since how long has this been going, but we will see. Um, okay, so what happens here is that we have packed this, and then what we do is so just remember that we had this RVE in the beginning. So it is 100 by 100 by 100. We see the grain size and they are oriented in a certain direction. If we want to see another case, so this. Now, because we have precipitates, I am expecting they will be distributed on the grain boundaries, and we will see what does it look like now. So I will import this. I will click on this. Okay, it is imported. Uh, Surface um, phases, first phases, right? So if I will see phases here, I should only see one phase, right? If I click on map schedules, right? So I see only one phase because there was only one phase available here. Okay, but now because I have generated multiple phases, if I see that, I see two phases, blue and red. So blue is basically the metrics, red are basically the particles that are visible here. Then if I want to see feature IDs, what I do see is that there are features that are, for example, like the grains, and then there are smaller features, for example, that look like precipitates. Okay, so this is also reasonable. Then, for example, I can look at IPF colors. For that, I have to click on this, and then we see quite random distribution, and then grains, and then precipitates embedded in them. So this is how basically we generate that. Now, my expectation or the idea is that if I keep the precipitate size same and its composition same, but I just change its um, 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 if I and what you will also see is that almost all the precipitates are on the grain boundaries. No, but almost all of them are on the grain boundaries. That is what we initially decided. I think these are two grains. Yeah, so these are two grains. Almost all the precipitates are on the grain boundaries. That is what we intended in the beginning. Okay. And now what I want to do is I want to change my um, I want to change my um, features in the Dream 3D to see what effect they will have. Um, I want to keep the precipitate size the same, the distribution the same. Um, Maybe what I want to do is I want to change um, what I want to do is I want to change the no. We can change certain things. What we can do is I want to change this size. Let's say make it 4.5, 4, and then make this 5. Now our mean feature estimated sphere diameter has changed, increased a lot. For the particles, I do not want to change that. Um, but let's say for particles, I change their orientation. So I change their orientation to brass, and it updates. I create data for this. I create data for this, and then I run my pipeline again. And what I'm expecting here is it is struck. But what I'm expecting here is that my matrix grain size would significantly increase, and my precipitates will still remain the same, but they will have a specific orientation, a preferred orientation, and then I will be able to see that in the end. And that is basically what my expectation is. The idea is that you will be able to manipulate certain microstructural features in two-phase microstructures, and you will be able to generate um, the 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 desired microstructures synthetically. Okay, we will look into this, and then we will see how you can um, come to generate representative volume elements for additively manufactured components. But it's not working. Can I? I cannot even cancel. Uh-uh. It's struck. It will take time. Or what we can very easily do is Control S, close it, and try running it again. Okay, file open. I want to go here. I want to do this. And I think the problem was, I remember what was the problem here. Um, I don't want to have this. Why? This is radial distribution plot. Hmm. Cubic cement type 0.2, let's say. No, it is not primary. Uh-huh. It is cubic 0.2. It's not primary, it is a precipitate, and it is tight. And then the fraction on the phase boundary is 0.5. What I want to do is I want to make it a little bit bigger this time. So yeah, somewhere here. Yeah, and then I want to create this data. And for this case, create this data. And then Okay, run the pipeline. Now I have less features, so hopefully this will end better. Okay, and then if I open my folder, I have this, and my parallel looks like this. And if I look at my microstructure, it will look like this. And here, so my faded grains are quite large. And then I have my precipitates, 50% of them are on the grain boundaries, 50% of them are within the grains. That's what we that's what we decided. And now the amount of precipitates is also more, so it is 20%. And this is what we can easily see here. And these are IPF colors. So what I can do is I can click on this and then we see all these different colors according to different perspectives. So from the X perspective, right? So they're all aligned in this direction, and this is what they this is what they look like. One more thing that I want to show you is that if you want to um, generate Dream 3D files directly from here, um, if you want to generate DAMASK files directly from here, um, the idea is to the idea is to there is a search thing somewhere here which I'm not able to see. No? Um, so if I, for example, click on this, I see that I have export Damask option, which is point-wise or grain-wise. And for example, if I click on grain-wise and I choose the folder, which will be the same, I can two phase example. Homogenization index is one. I click on OK. What I have to do is I just have to choose these pins. So feature IDs are here, Euler angles are here, phases are here, and then I just when I click on this pipeline, it will generate this as well as it will export it as a Damask simulation file for Damask 2. It is again struck. I'm not sure what is happening. And for example, now in this folder, you will see that I have this file and there should be one more file, geometry file. So this file, these two files are extra, which are generated. And in this material configuration file, you will see all the details related to material, grain wise, right? And then here we have to put all these homogenization crystalline phase things. And there is this geometry file which creates this kind of file which we can then use to later run crystal plasticity simulations. There is also a possibility to, for example, directly export mesh files for Abacus. right? So export abacus surface mesh. If I will double click on this, it will create a mesh file for abacus. So we can also do that. Um, and this file name is abacus test. And this is now then again an INP file, which then can be used. And I have to just give it face labels. Triangle data container is needed. Someone will have to look into this. So there has to be a pipeline component here to create um, triangle data container. And once this is done, then this kind of file can also be exported. I will just delete that. But that's basically the idea around generating different single phase or multi-phase microstructures using this. And what you have to do is basically you have to adjust these statistics such that they represent your actual microstructure when you want to create a representative volume element. And that's generally about it. You can have multiple phases here. You can adjust their fractions. You can click on plus and plus. You can add more precipitates here. What you can do is you can also adjust their sizes, size distributions. You can also adjust their orientation distribution functions, their grain lengths. So what I saw was, for example, I can open this. I can open this, the softwares, Dream 3D, pre-built pipelines, workshop, synthetic, cubic phase rolled. And if I just quickly run this, we will see that probably we will have a rolled microstructure. Um, uh-huh, rolled. So the size is bigger. Surface, and what we see is, for example, these grains are elongated in this direction, and then they also have a certain texture associated with them, right? So you can create kind of these kind of elongated grains. And for example, in case of additive manufacturing, you will see a microstructure which is in which the grains are not aligned in the rolling direction, but in the bend direction. See something like this, with some precipitates in between, and that will basically represent the microstructure. So the idea is you can look at these examples and see what they're doing here. So the orientation distribution function is the same, but you will see that the axis orientation distribution function is the one in which they have elongated the axis in the build direction, right? So in the x direction, so all the grains are aligning in the x direction. So this is the weight is quite high, and that is how the grains get elongated in this direction. And then the rest of the pipeline is just the same with synthetic volume size of 128 by 128, and the rest everything is same. And then you in the end get this kind of microstructure, right? And now you will see that it has specific grain size, specific orientation distribution function, but now the grains are elongated in a certain direction instead of being equiaxed. Um, so yeah, that is generally the introduction to Dream 3D, what it is, how you can change certain things, and then yeah, thank you so much.
I want to do is I want to stop recording.